Okay, so now we're going to look at this Hardy-Weinberg's law, okay, because we keep on talking about the population genetics. We talk about the allele frequency. So how we can actually measure allele frequency, how we can actually, from allele frequency, we will be able, okay, to get the genotype frequency as well as the phenotype frequency. So that's very, very important. Then we can look at this Hardy-Weinberg's law. Okay, so we use this Hardy-Weinberg law. It's a very, very old law in this case, very, very old law, but yep, it's very, very let's say that's it's quite useful in this case if you want to actually check for the allele frequency. Okay, so but there's many assumptions here. Is if you want to use this Hardy-Weinberg law, basically the populations must achieve what we call the genetic equilibrium. Basically, there's no change in the allele frequency. Okay, no point when you do it, the allele frequency, if you keep on changing, then the data won't be accurate, right? For example, today you measure the second day, then you want to use the data. Oh, data change already. Why? Because the change in the allele frequency. Okay, so here very important. You have to understand that it's a genetic equilibrium. So okay, so if we have the genetic equilibrium, so basically, if you measure, if you know the frequency of the allele, we can use this frequency of allele to predict the frequency of the genotypes as well as the frequency of phenotypes. Okay, so in this case, we're going to use two alphabets. One's P, one's Q. P, actually, we refer them to the allele frequency. Okay, P, actually, we refer to allele frequency of dominant allele. Okay, then Q, we actually refer to the allele frequency of recessive allele. So assuming that in the particular gene loci, particular gene locus, only a dominant and recessive allele, therefore P plus Q will definitely equal to 1, right? You try to imagine it's like your coin, okay, either head or tail, right? Even though it's a biased coin, okay, unfair coin, it doesn't matter, because no matter how you total up, the frequency will equal to 1 or probability equal to 1. Okay, so let us look at this, how we can use this to predict, okay, to predict this genotype frequency as well as the phenotype frequency. Okay, so let us look at this. Now, in one population, okay, if we look at a particular gene, so this gene have two allele. Let's say capital allele for dominant, code for dominant trait, whatever will dominant trait. Small allele A allele will code for the recessive. Okay, recessive trait. Okay, so in this case, if you want to know, okay, if we do have the allele frequency, let's say, okay, we want to find out what is the allele frequency, okay, of A. So I'll put it this P. So equal the probability of the capital A, okay, allele. So it's allele frequency, okay. So then Q equal the probability for the recessive allele, okay, dominant allele and recessive allele. Okay, so A code for dominant traits, small a code for recessive traits. So in this case, P plus Q will equal to 1. Okay, P plus Q will equal to 1. Okay, very, very clear cut. So what's P? P basically is allele frequency of dominant allele. Q also allele frequency. Okay, allele frequency of recessive allele. Okay, so P plus Q will equal to 1. But when talk of P and Q, they are in haploid stage, right? Because when you look at the cells, okay, so this is A, for example. Okay, the chromosome A, right? Okay, in the particular populations, but this is haploid. But when you look at 2 chromosomes, you're going to inherit small a allele, for example. So if you breed, okay, or cross between big A, small a, and big A, small a, heterozygous cross heterozygous, okay, then we do know that we're going to have the gametes with big A, gamete with small a, gamete with big A, gamete with small a. Kind of. So what are the possible genotypes? So possible genotype that form, you can see that big A and big A form big A, big A, big A and small a, you get big A, small a, okay, and then small a, big A again plus small a, big A, and then small a, small a. So in this case, you can see that I can simplify with a double big A, 2 times big A, small a, and 1 times small a, small a. These are the genotypes. So if A is the dominant allele, so it means that to inherit both copy of big A, it will be P multiplied with P. Correct? Big A is P, they multiply with P, small a is Q, and Q, small a, the allele frequency is Q times Q. And these, they are all, right? These 4 different kinds, or these 3 different kinds of the genotypes. So therefore, if you simplify the formula here, if a P square plus 2PQ plus Q square, definitely again will equal to 1, right? Okay, you will develop the formula here, P squared. Why? Because it's the haploid. So what is P squared? P squared represent what? P squared actually represents the genotype frequency. Genotype frequency for what? Genotype frequency of homozygous dominant. Okay, so 2PQ will be genotype frequency for what? For heterozygous. Now here, I want you guys to highlight here, very important, student always forget it's PQ, they put PQ in it. So be careful, it's 2PQ. Okay, so what's the Q squared? Q squared basically is a genotype frequency. A genotype frequency of homozygous recessive. Can you see that? So P square represents the genotype frequency of the homozygous dominant. 2PQ represents the genotype frequency of heterozygous, and then Q square represents, okay, the frequency of the homozygous recessive, and all them plus together equal to 1. Okay, but if you look at detail, big A, big A, big A, small a, both of them, they are dominant. They show dominant trait. Small a actually give us the recessive trait. Okay, show us recessive trait. So means that if I combine P squared plus 2PQ, then we combine together, this is the phenotype frequency of dominant trait. Okay, and then Q squared is the phenotype frequency of recessive trait. So it means that we from allele frequency, we start with the allele frequency here, P and Q, then we develop to get the genotype frequency, the green color, and then from the genotype frequency, then we can continue to calculate the phenotype frequency. Let's say, for example, so you will know that, okay, allele frequency. Okay, let me give a scenario first. Let's say, so big Y allele code for yellow seed, small y allele code for green seed. For example, if we do know that allele frequency for yellow seed, okay, equal to 0.4, for example. Okay, so question A. what is the allele frequency of green allele? B, what is the genotype frequency of number 1, big Y, number 2, big Y, small y, and number 3, small y. And C, question C, what is the phenotype frequency of number 1, yellow seed, and what is the phenotype frequency for green seed? Can you see that? Okay, so we have these 3 different questions. So to solve question A, so green allele, so frequency for green allele, which is equal to P for small y. So this one equal to Q. So in order to calculate Q equal 1 minus P. So 1 minus 0.4, so Q equal to 0.6. So it means the allele frequency for green is equal to 0.6. Okay? Now B. In order to get what is the allele frequency for big Y, so allele frequency for big Y will equal to P squared. So P equal to 0.4, so 0.4 square. Okay? So you get 0.16 per knot. Okay? So B1. B2. So what is the probability for big Y, small y, heterozygous? So heterozygous here, I use a different color so that you have to remember this 2PQ, not PQ. It's a 2PQ. Okay, highlights here. Always student confused. Okay, or forgets about the 2 that I put PQ. This is wrong. Okay, 2 times. Okay, so equal to 2. P is 0.4. Q is 0.6. Okay, so 2 times 0.4 times 0.6, so you get the answer 0.48. So number 3, if I want to know what is the probability for the homozygous recessive, we have 2 ways to do this. Either we use 1 minus the remaining one, or we know that it's equal to Q squared. So Q is 0.6 square. So 0.6 square, you get 0.36. Can you see that? Or you can use that probability of small y will equal to 1 minus probability of genotype frequency for big Y minus probability for big Y, small y. So 1 minus 0.16 minus 0.36. Yep, you are going to get 0.16048. Yet you get 0.36 as well. Okay. So next, C. So what is the probability or phenotype frequency for the yellow seed? So for yellow seed, this is the, when talk about yellow seed, right? Okay, yellow seed. If yellow seed is a dominant trait, so dominant trait formula will be P squared plus 2PQ. So 0.4 square plus 2 multiplied 0.4 multiplied with 0.6. Okay. So you get 0.64. This is probability or allele frequency for yellow seeds. So same thing, if you know that, okay, what is the probability for green seed? C1, C2 for green seed, then will equal to Q square. So Q, what's the Q? Q here, just now I calculate it. Q equal to 0.6. So 0.6 square equal to 0.36. Or alternatively, you can use 1 minus. Okay, then you'll be able to get the raw answer. So I put it smaller so that you can actually copy down if you need, or you can also take a screenshot if you need for this. Okay, so I stop it for a while here, then you know that this is the basic. Oh, sorry, I think that's, I need to move it here a bit. Okay, so I highlight the 2 PQ there, right? 2 PQ. Okay, now, even though we look at it, quite simple to do this. Okay, correct or not? We think that, oh, so simple when do this, but the question here is how we know the allele frequency first. It doesn't make sense here, you know, how you know allele frequency first, right? In normal research or normal study, you won't be able to know the allele frequency first. You won't be able to know, okay? You will know what? When you go into, let's say, for example, you check for humans blood group, you won't know what is the IA, IB, right? IA how many, IB how many? You don't know. What we know actually is based on their phenotypes. So in reality, what we do actually is opposite way. So what is mean opposite way? For example, okay, so this is example 2. Now let us look at this. Now if I go into the okay, into to survey, okay, a population, right? Populations of the mouse. Okay, I look at population of a mouse. Okay, so now the mouse have 2 different color codes. Let's say, for example, brown and white. Okay, check the populations. So mouse have 2. I've got a brown and also white. Okay, brown and white. And we know that in this case, brown is the dominant trait. Okay, we do know the genetic behind. Brown is a dominant trait, so white is a recessive trait. Okay, then if I'm going to check the mice, okay, I'm going to check the mice. Let's say I capture, okay, 1,000 mice. Okay, 1,000 mice. So 490 of them are brown color. Wait, let's say 1,000. Okay, sorry, 500, 500, if I check, sorry, 510, they are brown. Okay, they are brown. So means that if you look at this, how we solve? If I want to know, okay, so question A, what is the allele frequency of brown allele and white allele? B, what is the genotype frequency for each genotype? Okay, can I see that? So out of 1,000 mice here, 510, they are brown. Okay, and the remaining ones are white. So from here, how I can calculate the allele frequency and also the genotype frequency. Okay, so now let us start. First A. Always remember, if you choose dominant trait, we're going to get into trouble. If you choose dominant trait, we have the trouble here. Why? Because if you look at probability for brown color equal to 510 over 1,000. But brown, if you calculate the phenotype frequency for brown, it will be p squared plus 2pq equal to 0.1510, which is we won't be able to count. Why? Because we have 2 unknown here, p and q. We won't be able to calculate. So don't choose dominant trait. We always start with recessive trait. Okay, so we choose a recessive trait. So recessive trait. So probability for the white mice. What is the phenotype frequency for white mice? No, not white allele, white mice, okay? White color for white mice. Okay, white mouse. So it will be equal to 1000 minus 510 divided by 1000. So why we choose a recessive trait? Because recessive trait, we know that it must be Q squared. So Q squared equal to 0.490. So now we know Q. So Q equal to square root of 0.49, so equal to 0.7. So now I know. So what is the allele frequency for white? For white, so equal to 0.7. Can I see that? Allele frequency for white will be 0.7. So what is the allele frequency for brown? Because we know that it must be 1 minus, okay, frequency for brown, which denoted by P, will equal to 1 minus Q. So 1 minus 0.7, so answer 0.3. So now we have the allele frequency for white and allele frequency for brown. Then I can go for the second question now, B, what is the genotype frequency? So if a genotype frequency, for example, if the genotype frequency for homozygous dominant, then equal to P squared. So 0.3 square. So you get 0.09. Okay, so probability for heterozygous then will equal to 2PQ. So P equal to 0.3, Q is 0.7. So you get the answer 0.42. And what is the probability for the homozygous? If the question asks, normally question one asks homozygous recessive because we have done it already. Okay, so we're equal to 0.4, 1 minus all of them, or you can see Q squared. So Q squared just now we already gotten the answer. So 0.7 square. So 0.49. Okay, as I say that questions seldom ask for this. Why? Because we already have it here, Q squared. Can I see that? Question seldom asked. Question always like to ask which one? Heterozygous. Why heterozygous? Because student tends to forget the 2PQ there, eh? The 2PQ. Okay, so I zoom it, I make it small. Perhaps I can move it to the side. Oops. Okay, so this is example 2. Oh, sorry. Okay, so you can copy down the example 2. Okay. Now we go back to our notes here. So highlight these two formula, but in the exam, these two formula will be given. So again, these two formula will be given. And then what you need to do, you can continue with, okay, activity 15.11. So here we have a few questions for you to try, but this is a bit special because you cannot use P plus Q equal to 1 because we have 3 types of allele, IA, IB, and IO. So try to use a very creative way to think about it, okay? Now, highlight this 15.12, this activity, because question always asks, because we do know that Hardy-Weinberg always state that you must have the genetic equilibrium. You must have the genetic equilibrium in the population. If no, then whenever you calculate it, it won't be valid because it keep on changing. If the allele frequency keep on changing, so no point you count. You calculate also only for that particular moment. Okay, so what are the situations where this Hardy-Weinberg's law does not apply? Okay, when there is a small population. What do you mean small population? Try to imagine that if, let's say, we have 3 chicken or 4 chicken and then you assess it, it won't be valid because statistically it's not enough. The sample size is too small for us to make a judgment, right? For example, you throw the coin. You throw the coin 3 times and you get 2 head, 1 tail, and then you claim that, oh, it's a biased coin because 2 times head, 1 time tail. Okay, right? So it won't be valid if the small population. Okay, so if the mating is not random, now why is random mating is very important? If that is a selection of the mate in this case, then you can see that a particular phenotypes won't be able to be passed on to the next generation. So mating must be random. Okay, and you have to make sure there's no mutation. Why there's no mutation? You won't be able to see whether mutation take place or not, but if mutations take place, then we can know that mutation will create a new allele into the particular population and change the overall allele frequency. Okay, migrations and immigration as well, move in and move out, also will change the allele frequency, and this will cause the gene flow as well, right? And the last one is if there is a natural selection. When I talk natural selection means that you change the survival of the particular trait, and then you were going to affect the chances for that particular allele to be passed on to the next generation or not. So it doesn't matter whether natural selections or artificial selections, as long as you involve the changing of the allele frequency, then Hardy-Weinberg's principle won't be able to be applied. Okay, so now, but why we still, because look at this, the term and condition is so strict, right? Okay, so in nature, normally we know that Hardy-Weinberg's law is very rarely meet. Okay, the principle, right? The conditions here, very, very rarely we can meet this. But why we still use this law? When we want to check whether is there any evolutions take place or not. So we do a time point study. We do a time point study. Let's say we start in 2000, year 2000, and then 2005, and then 2010, and we continue to do like this, and we check for the allele frequency. If you can see that within this 10-year allele frequency doesn't change much, then we do know that this population actually at what we call the genetic equilibrium. But if, let's say, you can see a particular allele keep on increasing in terms of the allele frequency and another allele decrease in the allele frequency, then we do know that evolution may take place. The changing of this the phenotypes here, okay, tends to adapt to the change of the environmental factor. So that's the entire populations will be more adapted to the change of the environmental factors. Okay, so with this I have done for the Hardy-Weinberg's principles. Okay,